NASA's Jet Propulsion Laboratory presents the Von Karman Lecture, a series of talks by scientists and engineers who are exploring our planet, our solar system, and all that lies beyond.
Hey, good evening, ladies and gentlemen. How's everyone tonight? Thanks for coming to visit us. We really appreciate your attendance. So over the last 15 years, a miniature revolution in space science has been underway. CubeSats. First flown as educational tools the size of soup cans, significant capabilities have now been developed to allow these nanospacecraft to travel to the moon, asteroids, and even Mars. Tonight, we'll talk about how NASA, other companies, and students are building and flying small spacecraft and what types of missions they're attempting. Tonight's guest is a mission architect at NASA's Jet Propulsion Laboratory in the Planetary Mission Concept Group. His current research focuses on deep space nanospacecraft science and implementation. He is also the principal investigator on the INSPIRE deep space CubeSats and chief engineer of MARCO, the first nanospacecraft headed to Mars. He also supports robotic and scientific research in the Arctic, including a novel buoyant rover which explores underneath lake and sea ice. Before starting at JPL, he served as a postdoctoral fellow at the Japanese Aerospace Exploration Agency, JAXA, as a member of the Hayabusa Astrodynamics team and an Icaros mission team member. Prior to JAXA, he was a postdoctoral fellow and chief engineer of the University of Michigan's Radio Aurora Explorer CubeSat project. He received his PhD in aerospace engineering, master's degrees in space systems and aerospace engineering, and bachelor's degrees in aerospace and electrical engineering, all from the University of Michigan. In all that other time he scuba dives as part of the California Science Center Aquarium Dive Team, is an adjunct professor at Arizona State University, works at Space Camp in South Korea each summer, is an instrument-rated private pilot, and finished the Ironman Lake Tahoe in 2015. Yeah, he's not busy at all. Ladies and gentlemen, please help me welcome tonight's guest, Dr. Andrew Klesh.
Thank you, Mark, and thank you all for coming tonight to JPL. Here at JPL, we explore the furthest ranges of the solar system, and yet we also support activities right here on Earth, near Earth as well. In fact, just above our heads right now, we have the space station overflying the Earth and providing a unique observation capability, one that is unmatched in terms of its size and its breadth. Yet did you know, on board the space station itself, there's actually a spacecraft launcher on board, just on the side of the Kibo module provided by the Japanese. And if we take a closer look at this particular launch on here, it's not just one spacecraft coming out, it's actually two small spacecraft. Now, the small spacecraft that are on here are really the subject of tonight's talk, and are really opening up how we're exploring the solar system. When we take a closer look at these, they really are quite small, only about 30 centimeters long and about 10 centimeters wide. And this is one of the bigger ones. When you open these up, however, they really do expand. Everything from solar arrays to deploy, a telescope on the front end, solar panels, and an antenna to talk back to Earth. So every one of the large spacecraft you see around here are made up of the same components that we have right here. Only in this case, we don't launch just one, but 28 different satellites launched together to make a constellation around the Earth. Far cheaper and far more focused than what we've done before. When we start digging into some of the nomenclature, some of the names that we give some of these different spacecraft, we like to talk about them in terms of units, or U's. A 1U is 10 centimeters on the side, 10 by 10 by 10 centimeters. And to give you a sense of scale, this is a 1U spacecraft. And it's actually double the size of some of them that have flown. Next to that, we have 2 units, about 20 centimeters tall, or 3 units, a full 30 centimeters in height, but still 10 by 10 on there. In comparison, Juno is 20 meters wide. And in a little bit more direct case, we talk about soup cans, loaves of bread, and a tour bus. This really is about the same size on here. So these CubeSats look like they don't have a lot of capability. But over the last years, we've really been developing what they're able to do. Now, not only are they small, but they're pretty lightweight. So many of the spacecraft that we have exploring the solar system range from about 500 kilograms up to over 10,000 kilograms. These are incredibly large spacecraft and take dedicated launch vehicles to reach orbit and to explore further. There's a whole class of vehicles, though, that are a little bit smaller, and we do call these small spacecraft. Definitions vary, but somewhere in the 500 kilogram range and down we have small spacecraft. And within there, picosatellites, nanosatellites, and microsatellites. And everybody somewhat comes up with different definitions here. CubeSats fit within this picosatellite to nanosatellite category on here. So you'll often hear me say nanospacecraft or nanosatellite, and CubeSat along the way as well. But not only are these things small, but they actually enable us to launch many more of them. So since the year 2000, we've had an explosion in the number of spacecraft that have actually been launching. With CubeSats alone, you can see they started small at the first invention and have just exponentially been climbing in terms of the number of launches that we've had and CubeSats deployed on orbit. And it's not only one type of institution on there, but everything from universities, which really developed this standard, to the military, civil, and NASA, as well as commercial entities are actually launching CubeSats and accomplishing important missions around this world, and now further out from there. Now, the CubeSat itself goes back to these two individuals, Professor Bob Twiggs, previously at Stanford University, and Professor Jordi Puig at Cal Poly San Luis Obispo. They had a fundamental thought near the end of the 1990s on here. They recognized two important facts. First of all, they recognized that everybody is carrying a satellite in their pocket. If you look at your typical cell phone, a lot of electronics have been miniaturized down from the large boxes of the 1980s to something that we carry around every day. We have a payload on board in your camera, power storage in terms of the batteries that are there. We even have a way to charge those batteries with a connector on the back end. We communicate, whether it be text or wireless, Wi-Fi or cell phone. And there's a massive computer on the inside that is now just the size of your thumb. Some way they can actually determine your attitude, whether you use it for a compass, or even your position when you use the GPS in it to determine where you are and drive down the street. So all of this capability is now in your pocket. Imagine what we can do with that capability when we put it in a spacecraft. They also recognize the second thing. No one wants to launch something that's uncertain. But if we can define a box and isolate what's inside that box from, say, a bigger payload on there, maybe they'll let us carry it along the way. In fact, many large rockets actually carry ballast with them. They balance out the spacecraft on there that's riding on top, and this ballast is little more than dead weight. Let's make that dead weight actually intelligent. Let's do something with that dead weight along the way. To be able to do that, they came up with a dispenser called a P-pod, or polypicosatellite orbital deployer on here, that would contain anything inside there and isolate it from that larger vehicle it might ride up with. So we made a standard bolt pattern so you can put it on any number of different rockets. We made it so that the satellite inside did not turn on until deployment, again, keeping it totally isolated. And then we made a very easy way for it to get away from that bigger rocket just by pushing it out like a spring. Really, it's a jack-in-the-box, except we have a satellite on the inside. This simple method, along with the electronics miniaturization, opened up the launch market and made these small satellites actually able to get to orbit in a standard way only by following a 6-page specification. Very little paperwork along the way. Now, ULA is one of the large launch providers that's out there, United Launch Alliance. And they recently published a specification on what happens in a CubeSat mission. You have a large rocket that's launching up there, and it deploys a primary payload. Maybe it's a telescope or an Earth observer along the way. Once that's deployed, these P-pods actually spring forward and push out the small satellites, or CubeSats, that are in here. Each CubeSat performs a mission around the Earth. And as we were talking about, these 1Us, 10 centimeters by 10 centimeters by 10 centimeters in size, come out to be very, very small. And to date, ULA has actually launched 55 individual small CubeSats on board. Overall, we've launched over 400 CubeSats in the last 15 years, each of which is performing a different mission on there. So what is a CubeSat? A CubeSat is really a containerized payload that is conforming to this small, simple standard. And this standard has been pre-approved by all these different launch vehicles on there. As long as you stay within this standard, you can launch virtually anything. If you start to violate the standard, then you're going to get into the realm of expense, risk, or reduced mission. The properties of the CubeSats are worth talking about on here because the CubeSat is only a specification within this realm of small spacecraft. Most CubeSats that you see are around the range of nanospacecraft here, adhering to this CubeSat spec, and you can download it yourself. It's open source and widely distributed. They generally have a very focused mission objective. Many spacecraft we have around the Earth are looking at all sorts of different sensor data and returning great amounts of science. A CubeSat is typically looking for a single thing, and in conjunction might create a large amount of science measurements. But in general, it's got a very focused mission. They're also generally low cost, and this is extremely attractive. We can have university students. Heck, we now have an elementary school that is making a CubeSat that will be launched in the near future on here. And yet at the same time, the very fact that they're low cost means that they are attractive to commercial folks, to the military, and to institutions such as JPL. Being low cost, it often means that we can actually accept increased risk. Now, when we have a very large vehicle, it's very expensive, and you don't want to make more than one of them. If you have something this low in cost, then you can make more, and if one fails, you launch another one up there. That is a massive improvement over what we've done before with our larger spacecraft. But it does take some looking at. With any mission, you have a few trades that you have to accomplish. You're often trading against the risk choices and the number of mission requirements that you have for a given cost number. A lot of times, scientists like to add requirements. They want to look at one additional thing, or they want to add one more instrument on there. And every time you start to add additional requirements, it means that you go out of balance. Something needs to change in order for you to accomplish your mission, given those additional requirements. And with CubeSats, we typically accept additional risk along the way. So we add the risk, and we actually can get back in balance on there. But that's not the only thing that we can do. Oh, this took a little while to make, so. We can also change the budget. We can add money on there. If we add the money, maybe we don't have to add that additional risk, and we can still stay in balance on there with the same amount of risk. Or we can go to the scientists and beg and plead, and we can actually reduce the number of requirements that we have to bring us back into balance. We do this with larger missions all the time. But if we're coming in with a very small budget on there, that means our mission requirements have to be very low, and we have to accept more risk to maintain our balance. Back in 2003, some of the first CubeSats were actually launched. This is Psi-4 from University of Tokyo. Actually, 13 years on, it is still returning images from orbit on there, blowing away anybody's expectations. The first thoughts were that we'd only have a few days on orbit. And CanX-1 from UTIUS up in Canada. They launched together with similar missions and similar capabilities, but actually Psi-4 is still operating where CanX-1 failed early on. That didn't stymie the students that are up there, and they have launched so many more CubeSats since that time, learning themselves, increasing the capability of the lab, and have had many additional successful missions since that point. Later on in the 2000s, we had Ames come through with a whole series of different spacecraft, where they actually were looking at astrobiology, everything from seeing how bacteria survive in low Earth orbit, to doing a controlled yeast growth, and actually looking at the survivability and viability of organics. And each mission learned from the previous, creating a very rapid cadence of scientific knowledge being brought forward. Late in 2008, 2009, the National Science Foundation became involved in the CubeSat movement. And around that time, they said, we want to actually do scientific CubeSats. No more will students be the only ones to create these small vehicles and take advantage of the launch availability. And this is a particular CubeSat that is very close to my heart as I worked on it back at the University of Michigan, known as the Radio Aurora Explorer, that had a focused mission to look at and investigate these irregularities in the upper ionosphere by passing overhead and having a radar beam pass up through the irregularity and be collected by the small spacecraft. Too low for the other observers that we had up in the sky and too focused for them to really develop a dedicated mission to it. The CubeSat fit the bill and provided a number of scientific journals that were out there, leading to Therese Jorgensen to actually say that this has convincingly proved that small spacecraft can provide high caliber measurements and scientific return. Now, around that same time that the science value of CubeSats was validated, we also had NASA become more involved with the CubeSat Launch Initiative. This is actually where NASA will provide free launches to those coming from educational institutions, government centers or just NASA centers overall. It is if you adhere to certain requirements on there and if you go through a application and down select process along the way. To date, there's been over 9 launches with many more scheduled in the near future. And this free launch has brought down the cost of the CubeSats even more, either for the scientific return or for the students that are getting the educational benefit out of them. So the launch program exploded at this point. The Falcon 9s from SpaceX were launching. ULA was launching CubeSats on there. We were going overseas to the Dnepr in Russia, and many other people were also launching CubeSats, providing a boom in launch availability. But the CubeSats themselves continue to develop. What started as simple one-use that were only imagers on board have increased immensely in capability. This is a recent CubeSat that's being put together. It's actually the innards down below as well as the outer shell, built by a company here in Southern California called Tyvak Industries. Now, Tyvak is actually going to have 2 CubeSats launch independently, find each other on orbit, rendezvous in that same area, then dock together, separate again, and do this repeatedly. This is all in the size of a loaf of bread that can now maneuver around orbit, and imagine what we can do with this capability on here. In fact, this is one of the test sequences that they have where the 2 satellites actually dock together and grasp each other. And then these small mechanisms can actually release again and separate the 2 CubeSats to the side. They're getting ready to launch just in the near future now. Now, that's nice as a 3-use size, but we're actually doing that same or a very similar capability in 1.5 use, only 15 centimeters high. I ran out of room to put all the different things that are in this spacecraft, but it includes laser communications down to Earth, multiple cameras on board and a suite of different sensors, a thruster system so they can actually maneuver around and orient themselves. And it's all to really study optical communications and proximity operations for a low cost, not necessarily so we can only do it on CubeSats, but so that we can take all of this technology and use them on our larger vehicles as well. Bringing down the mass in any individual instrument means we can bring it down for every spacecraft that's out there, increasing all of our capability. These guys are launching 1 or 2 at a time, and they have several launches per year. But in the commercial sector, there's a whole other type of revolution going on. Planet Labs, with the flock that you saw earlier, is launching 28 CubeSats at a time from the space station and have around 130 already on orbit with another 28 sitting on the space station right now, just waiting to deploy. With these different spacecraft on here, they're actually looking to do very rapid imaging of the Earth. And with this rapid imaging, though the resolution is not as good as what you might see on a larger spacecraft, they're able to get great temporal coverage. Imagine being able to look overhead at all of your competitors out there and see how many cars are in their parking lot at any point during the day. You'll actually be able to determine how well they're doing their business and how well your marketing might do, or how the agricultural fields are doing in any given area, given storms that are passing overhead. There's a whole wealth of knowledge that they're collecting, and it is that knowledge and the data that actually drives their commercial success, where the CubeSats are the tool to get them there. When you compare these against some of the larger vehicles that are out there, Worldview and Landsat that provide many of the images that we use on Google Maps and other such programs are far larger, around 2,000 to 3,000 kilograms. These CubeSats weigh about 5 kilograms, and we're launching all of them at the same time to get better coverage, and really the resolution isn't bad when you're looking across there. But these aren't the only commercial fellows that are out there. In fact, while ULA and while SpaceX have often provided launch opportunities, there's a whole market that has sprung up around just interfacing to the vehicle. If you have 28 different spacecraft that are going to launch together, you need someone dedicated to integrate those onto your launch vehicle. And that's what Spaceflight Industries and several other companies have done. That you can actually go to their website, you can get a quote. What will it take for me to launch my spacecraft to orbit or beyond? And beyond that, there's a host of all different companies that are out there. And this is only a very small selection, offering CubeSat components. If you don't know how to build a CubeSat, you can buy the whole thing, or you can buy parts of it. You can develop parts in your lab and integrate them with others. And here at JPL, it's this community that we've partnered with in order to even go beyond the solar, or beyond the planet Earth. So in low Earth orbit, we've greatly expanded beyond what's in only a single one-use spacecraft on here. This is RainCube. RainCube has a 0.5 meter Ka band radar, active radar that's on there that expands out once it's on orbit. Because a truism with CubeSats is that you're only a box until you've deployed from that P-pod, and then you can expand into any shape that you actually need to. with two different solar panels on board, active attitude control to steer around, and the radar system here, we're looking at developing a new technology to look at the precipitation in the clouds and how that will affect the weather and other things here on Earth. Now that we're able to perform science here on Earth, we all began to question, how could we go throughout the solar system, and what else might we discover given the unique platform that we have? We looked at heliophysics and found that we could build constellations of 50 or greater spacecraft to simultaneously map out the solar winds far away from Earth and be able to better determine and better predict what happens when these coronal mass ejections or the solar blasts actually come to Earth itself. We've looked at going to comets, into areas that we would never dare send another larger spacecraft that was more expensive. Imagine going down into the plumes, going down to see the comet surface on there in that dangerous environment, and not worrying if you lost a couple spacecraft along the way. Send in the probes. Be just like Star Trek. And we've also looked at novel science opportunities. These are the areas that we've never been able to before discover because we didn't have the vantage point, or we weren't able to go by. With a single orbiter going by Pluto, with the New Horizons probe, we had one glance across the surface. If just before it had gone to Pluto, we had separated out multiple small spacecraft to simultaneously fly by, imagine what we could discover across the entire surface there. And that's just one body in our solar system. Now, the problem with going throughout the solar system on here is that it's big, and it is really, really big. I've defined things here in terms of astronomical units. And an astronomical unit is the distance between the Earth and the Sun, about 150 million kilometers. Venus is about 0.8 AU out, and Earth sits around 1 AU. When we're headed out to Mars or beyond, we often have to travel hundreds of millions of kilometers to get there, and then we have to talk to this thing. The problem with traveling throughout the solar system is that we're all reliant on power in some manner, and generally the power is coming from the sun. Now, the problem with power coming from the sun and light is that it actually degrades over distance, and it's not only proportional just to the distance from the sun that you are, it's proportional to the distance squared. So power drops off significantly as you head throughout the solar system. If we were starting at Earth, we receive half the power from the sun once we actually get to Mars. Now, along the way, the problem also occurs in communications, where it gets harder and harder to communicate as we head farther out. With that line of power, we also get colder. There is less thermal energy on our spacecraft, and so we have to deal with all of these challenges. And none of the CubeSats that I showed you before around the Earth really have to deal with this change in power or the horrid communications, the thermal that is changing on you all the time. So before we could take any of these CubeSats out there, we needed to have a precursor. We needed to show that we could actually develop the technology to have these miniaturized spacecraft head further into the solar system. And that is what Inspire did. Inspire, or the Interplanetary Nanospacecraft Pathfinder in a Relevant Environment, it's still NASA, we like our acronyms. It was actually a dual spacecraft mission, and it was to leave Earth orbit and head out about 1.5 million kilometers away from Earth. It's an important number. It's around the Sun-Earth Lagrange point, and it's about 4 times farther out than the Moon itself. Now, these guys really were just to drift out to 1.5 million kilometers and keep going after that. But they were to prove that we could communicate, that we could navigate, and then fundamentally we could survive with small spacecraft outside of low Earth orbit. And if we didn't have the technology to do so, we would actually develop that technology along the way. So Inspire is currently developed, excuse me, and is sitting on the shelf. And this is kind of what it looks like. In a 3U container, remember about the size of a loaf of bread, it actually has X-band antennas that we can communicate back down to the deep space network and provide data back and forth. We have a UHF link, so we can actually talk in between the spacecraft and pass commands, just as if we had been separated from a mother spacecraft further in the solar system. We crammed a science payload on board called a magnetometer to look at the magnetic field. And whereas Cassini has a magnetometer sensor that is about the size of a shoebox, this entire magnetometer is about the size of my fist, with a sensor that pops out in a small 5-centimeter boom, enabling us to look at the solar wind in the local Earth environment. We made an attitude control system, and here we took a risk. We actually made the attitude control system in a 3D printed part. The entire tank, all of the thrusters on there, and the valving, the pipes that go between them are 3D printed. In fact, we found we had more volume along the way as we were developing our design. And for $800, we actually doubled the tank size on there just by printing a new piece and putting it on board. We have a star tracker we worked with a company to develop that was slightly smaller than what was otherwise offered. And we had advanced computers that we'd actually be able to look at. Will we be able to survive? And if we can't, can we reset ourselves in an intelligent manner such that we can keep going, even though we had commercial, non-space hardened parts there? We developed a system that actually had the batteries and the solar panels on board for power. And most importantly, we developed the Iris X-band transponder. This is a communication system that allows us to navigate with the spacecraft and to communicate from data rates down at 62.5 bits per second, far lower than the early modems, all the way up to 260 kilobit per second, around the speed of some DSL lines that are out there. So these spacecraft are ready for flight and are sitting on the shelf now. In fact, they had a launch opportunity along the way, but in fact, something else stole it, and that was an unfortunate day. Several years ago, we proposed here at JPL to send a lander to Mars. And this was the InSight lander. It is currently now to launch in May of 2018 for a landing in November, and was to launch from Vandenberg Air Force Base. I say a little bit of past tense here because, as many of you might know, the InSight lander was actually supposed to launch a month and a half ago, but had some delays with the seismometer, and so due to planetary alignment, we have to wait 26 more months. But when InSight is actually ready to go, it will launch from Vandenberg on an Atlas V 401, head out on a cruise stage, and then go through that terrifying 7 minutes down to the surface of Mars, entry, descent, and landing. Along the way, it will be going through cruise, about 6.5 months as it's going out there. But once it reaches the surface, we're going to be looking at Marsquakes. We're actually going to be investigating and using the Marsquakes themselves to ring the planet and look at the interior of the planet itself based on the seismometer, as well as this mold that will go down several meters into the surface. This is an incredibly cool mission here, where we're looking at the internal of Mars, but we still have to get there. And as you might know, many Mars programs in the past have not made it all the way to the surface. In order to get around that fact, we established a rule here at JPL. We wanted to learn from any failures that we might have had in the past. Now this means that going through entry, descent, and landing, we'd like to get that data back in real time to know, did it survive, and how well did it do? Right now, we have a lot of different Mars orbiters around the planet over there, and typically we collect all the data with these different orbiters in preparation for sending it back to Earth. For InSight, the Mars Reconnaissance Orbiter would be collecting this information, but it collects it in such a broad band that it actually has to store it immediately on board and can't send it back in real time. On top of that, because of orbital geometry, it actually immediately after EDL passes behind the planet. And it's several hours before we'd actually know if InSight's alive or dead. To get around that fact, JPL proposed a new mission, and it's called MARCO. It's Mars Cube 1. And this was 2 spacecraft to launch with InSight on that Atlas 401 to actually separate only 90 minutes after launch and independently cruise to Mars over that 6.5 months to get there on just the right moment, on just the right day, in just the right spot, so that we could collect the data from InSight and relay it back in real time back to Earth. It has to carry out 5 different trajectory correction maneuvers. Because of planetary protection and other regulations, when we launch, we don't aim for Mars. In fact, we offset from it. So we have to somehow steer ourselves back to target to get there at just the right time. And then on that time, we're going to fly by the planet, collect the data from InSight, and somehow send it 157 million kilometers back to Earth. Now, we proposed we were going to do this with a CubeSat. Most CubeSats operate about 300 to 800 kilometers away from Earth. So we had a slight challenge here. But the team from Inspire and from others around the lab came together, and we started to develop the MARCO spacecraft. And this is a CAD rendering of MARCO. The engineering model is actually sitting over on the corner of the stage. And that's actually called a 6U in size. It's about the size of a Sam's Club cereal box. It's so small, actually, that the Pelican case that's next to it stores the spacecraft, and you can take it as carry-on on board. For our smaller spacecraft, like the 1Us, they fit underneath the seat in front of you. So MARCO needed to be a little bit larger. It needed to take a lot of capability to get out to Mars. This is a significant challenge to get out there and to relay the data back again. If we take off the front cover of MARCO and start to look at the inside, you can see that it is somewhat of a complicated and, more importantly, a dense system. We actually looked at the density of MARCO versus some of the larger spacecraft. And while most spacecraft have a density of about 0.7 with respect to water, MARCO is double that. We just crammed everything we could into this vehicle on here, and it was all to carry out the mission at hand. If you start at the top, you see the solar arrays. This is how we are collecting power along the way. And since they expand out, they actually have to be deployed once we escape from the P-pod, once we get out of that deployment box on the InSight rocket. We use that power to actually charge our batteries, which are about halfway up on the right-hand side. I can actually point those out on here. So the batteries are stored right here. And all that power from the solar panels, remember, it cuts down to about half of what it was here at Earth. About 35 watts here at Earth are collected by these, and only 17 watts when you head out to Mars itself. About half the spacecraft is taken up by the propulsion system. This is a cold gas propulsion system, and by cold gas, I mean it's a refrigerant that's on board. And it's a very special refrigerant that's in here, kind of the same that was in Inspire. In this particular one, it's known as R236FA, or FE36, and FE stands for fire extinguishant. It is actually the halon replacement fire extinguisher fluid that you'll find in many commercial fire extinguishers that are out there right now. If you've seen the movie WALL-E, we are WALL-E. We are spraying a fire extinguisher and going to Mars. Now at the top here, to get all this propellant out, we actually have 8 different thrusters. 4 of those thrusters are for trajectory control and actually steering us to the right location. 4 of them are actually for attitude orientation on there. And they're to work in conjunction with our reaction wheels, which are wheels that spin internally to the spacecraft and allow us to orient. We also have that all-important bit. Remember, we're a communications mission. We're relaying data back to Earth. And the IRIS radio here and X-band transponders, actually the 2nd generation, is the heart of the spacecraft and is collecting data at 8 kilobit per second in, and is sending that data out again over X-band at 8 kilobit per second out, down to the Madrid station of the DSN and the 70-meter dish. Here we have a 30-centimeter tall spacecraft talking to a 70-meter dish. I would love to get a picture of those two together on there, but it hasn't happened quite yet. We use amplifiers on here to actually bring in signal and raise the signal level up when we're communicating to the spacecraft. And we use a power amplifier to send the data out and back down to Earth as well. But we use some very unique antennas in order to get there. So you notice there's no large parabolic dish that you might see on Voyager or Cassini. We actually use something called a reflect array, and it really helps when you're trying to fit in a narrow box, where we have a small piece that sticks up on the top here called the active feed, and this is where the signal is transmitted, which bounces off this large deployable panel. And this panel on here is what focuses all that energy and sends it on a very narrow beam all that way back to Earth in the 70-meter dish. This thing has to fold in and fit on the top there, because this doesn't exactly look like a box when we're trying to deploy from the P-pod. We have a whole stack of electronics over here, all of our avionics. Everything from attitude control in those reaction wheels, a star tracker, an inertial measurement unit, basically the pieces that you might have in your phone or around there. The computer sits here in the power system, all of the interface boards and the harnessing that is throughout here. And we fit this all in the 6U container. Now we actually ended up having a little bit of extra volume. So like any good engineer or scientist, we decided to fill it. And in this particular case, we actually put 2 cameras on board. One is a very wide field of view camera that can capture both the deployment of the reflect array as well as look back towards Earth and see that small little dot out there in the sky. The other one is a narrow field of view camera looking downward towards Mars so that when we fly overhead with this small CubeSat, we're actually able to take images of another planet just off of something that's sitting right over there. We do need to collect that data from InSight. And I mentioned that it's UHF. So on the back, we have a deployable antenna, what's called a loop antenna on here. And we're collecting this data from InSight and then sending it on its way. So we have one antenna that has to point at InSight. We have another antenna that has to point towards Earth on there. And we're passing overhead at high speed as InSight's going from kilometers per second down to 0 on the surface itself. So there's a lot of pointing challenges that we faced along the way. Now also on the back is this bare area at the bottom on here. And this area is actually filled with some stuff. In fact, we came in lightweight compared to what we were supposed to be. We told our launch provider that we'd be about 14 kilograms, and when we built everything up and we assembled it all, we were too light. We were sitting around 12 kilograms. So I have 2 kilograms of tungsten sitting on the back of the spacecraft. That's 1.5 of these that I could carry along the way as well. So there's additional room for more payload on here, should we choose to find things or fly things on future missions. For now, though, they act kind of like a thermal battery and allow us to turn on systems on here in a little bit easier of a manner. It turns out, when you head out towards Mars, that you actually need a pretty powerful radio, and the propulsion system uses a lot of power as well. Any power that's going into a spacecraft is going to turn into heat in some manner. And while many large spacecraft have large radiators and a large surface area to dissipate that heat, in this particular one, we have about 100 times more heat, or 100 times more heat that we have to dissipate for its area compared to something like Juno. And so we have radiative panels on the back that were actually expelling heat, and we use that tungsten to slow down how quickly we are warming up. CAD models are nice, but you guys want to see the actual thing. So last July, we assembled an engineering model. Actually, it's the one that's sitting over there, in order to best test how we could put this thing together. Because you know, they didn't exactly give us a lot of time to build these spacecraft. From concept to readiness for flight, and it would have been launched, was less than 14 months. This thing moved incredibly fast. That meant we needed to make a lot of shortcuts along the way. If you remember that seesaw in there, we threw out some of the design analyses that are typical for larger spacecraft and said, we will rapidly prototype these things, whether it is through 3D printing or through other mechanical shops, such that we can build an early prototype and literally see if it fits together. CAD helped along the way as well. We were able to model all of this in the computer. But there were many lessons that we learned from assembling this, even where should the wiring and the harnesses go on the inside. At the same time, we successfully showed that we fit in the box. We could launch with our rocket along the way. And we started to get other pieces of the spacecraft in, including the thruster system that has those 8 thrusters to both steer us and orient us towards Mars, as well as the attitude control and the ever so sensitive star tracker. Now, a star tracker is kind of like a mini telescope that's inside, and the reaction wheels, or these spinning wheels, are on there. To give you a sense of scale and everything that's in there, that's a 1 centimeter cube that's sitting next to it. Again, we're talking about very, very small little pieces. We did go through many of the environmental tests that larger spacecraft go through. And here you have the flight model of the Marco, actually the first flight model since we were flying 2. When you look at the inside of the spacecraft, you can see it is a very dense little craft in there. And yet everything has a purpose and was able to get us to a successful mission readiness level. And now we're waiting for our launch opportunity to go with InSight itself. Here's the Marco family: Flight Unit 1, Flight Unit 2, and the engineering model that you see over on the side. But it is never only the flight models that you have to develop. In rapid prototyping and rapid development, or even on the longer scale, you always want to build something that, try it as a prototype on there. See that it works and have something to tinker with when you actually launch it out into low Earth orbit or beyond. And so we actually built another 3 or 4 versions of Marco, all at different levels of fidelity on there, in order to educate ourselves on how we should actually fly this craft. On the big day, once we actually get to Mars and InSight is going in for landing, it will be sending off its cruise stays and separating out, going through entry, descent, and landing. Now, as you know, InSight down in the lower corner here is going to hit that atmosphere at a blisteringly high temperature. Actually creates a plasma sheath on the outside. Meanwhile, Marco is passing overhead about 3,500 kilometers away, collecting the data that InSight is transmitting out, including when the parachute is actually deployed or when the back shell is released. Once that back shell is released, it's able to look down at the planet, start finding its actual place that it would like to land on there. And here the landing legs actually pop out. And remember, InSight is very close to Phoenix. It's actually not going to land on a parachute, but in a second you'll actually see it will fire rockets so they can come down to the surface. If that's not terrifying enough, remember it's going from kilometers per second speed down to 0, and this takes only about 7 minutes. So all this time, JPL is very interested. Did InSight survive, or did it not? Marco will continue to pass overhead. It does not enter orbit at Mars. It's in no way critical for InSight's success, but it gives us that additional information we need to make additional missions successful down the way. As well, these vehicles serve as a prototype for those missions that might take place with critical events that either go behind the planet itself or in otherwise difficult to see areas. InSight's going to be telling us all about the internals of Mars itself when it launches in 2018. And Marco's going to be there in the very beginning in order to tell us that it made it down for its successful mission. But while we're very excited about Marco and everything that's going on with that program over here, that's not the only thing that's happening in the CubeSat realm here at JPL. Whether it be in low Earth orbit, 3 spacecraft to go around the moon, we have a spacecraft using a solar sail that is actually going to go out and visit a small body object, an asteroid that's out there, or the Marco spacecraft that are going past Mars. This is really only the beginning. And these spacecraft are only a sampling of the ones that actually have funding here at JPL to go forward. And JPL is only one place in this broader CubeSat community. When we look at exploring the solar system, there are so many different unknown places that are out there, and so many scientific questions that we could answer. These days, we have everything from elementary school kids, high schoolers, college students, and graduate students that are looking to learn more about spacecraft before they come to JPL and before they start working in industry. At the same time, commercially, we're developing new markets for the data that we're able to collect by using CubeSats around low Earth orbit on here. And yet, as we travel throughout the solar system, we have a brand new platform, a new way of exploring if we take a little more risk or if we get a little bit more focus in what we're trying to do. And given the low cost, we can send many of these out here. So my question for you is, where would you like to go? Thank you very much. We are open for questions, if you'd go to the mic in the center, and I'd be happy to take any that you have.
Hi, yes, I have a question. This is very exciting, and I can see how this has just started and how it can all go in the long term. But what about security? What about, this is like, at one point it could become space junk. And how do you control that? And what if it collides with another bigger, like a space station or something like that? Just wanted to know how that goes.
So there's 2 aspects to security on here that I can address briefly. One is on the communications side and all the export control regulations that we have. And we, of course, with these spacecraft or with others, still have to adhere to those laws and regulations. Along with those laws and regulations is one particular one on orbital debris that says, for us, you have to be down and have burnt up in Earth's atmosphere within 25 years end of life. And before any spacecraft actually launches, there is a report and analysis that has to be done, whether it be a CubeSat or larger vehicle, to say that we will be able to do that. On top of that, the CubeSat community is actually developing technologies to enhance or to speed up that debris mitigation on there to burn up in the atmosphere. Many times we launch from the space station, and it's only a few months that we are on orbit. And the higher ones that are out there have to show that they'll get down. The nice thing is space is still very big, and we are tracking all of these spacecraft along the way at the same time, and working very closely with the government on how would we handle maneuvering and how can we safely operate these spacecraft all together on there.
Yeah. So say if one of these CubeSats goes rogue, right? I mean, now you're talking about many, thousands of them, right? So anything can happen. It might go rogue. Or there might be somebody puts a virus on it, and they might have programmed something into it. Would you have control to vaporize that thing out there?
So we have no control to actually vaporize these along the way. In fact, because of the criticality of trying to carry something like that on board, the primary launch vehicle would rather we not have that capability there. It's more to the point, though, that we look at the space. Most of the CubeSats that are out there have no ability to maneuver in space. They're on a fixed trajectory around. And that the ones that do have that maneuverability have to go through an increased set of both security constraints in terms of the communications and how to actually get it up to orbit on there, as well as additional look and interaction with the people who are actually tracking those on orbit.
Thank you.
Thank you.
Continue the theme of space junk. Can you give us
one man's junk is another man's spacecraft, so.
The range of orbits that these little things will fly, and also what are the range of prices are we talking? You talk about cheap device. What is the meaning of cheap? Yes.
Sure. So in terms of the orbits, most of the CubeSats that have launched go between about 300 kilometers up around space station level to about 800 or so kilometers up, just below the Van Allen radiation belts that are up there. And this has been a comfortable level. Of course, with Marco and Inspire and the future deep space ones, we will be headed out and away. and we call them disposal orbits in some ways. Second one is the range of prices. Early on in the CubeSat movement, when you had a craft that was not very sophisticated on there, many people were using off-the-shelf technology, and you could get launches for as little as $30,000 to $50,000, and the CubeSats in there, depending on how much testing you did, were on that same order of magnitude. These days, everybody's getting more sophisticated. The National Science Foundation typically puts out a grant of around $1 million or so if you were going to fly a science mission around the Earth. The Inspire mission for testing in deep space was about $5.5 million. And then headquarters is advertising that the Marco mission is about $13 million for us to actually fly by Mars and all the development that's there. So a whole range. If you could use the mic actually over in the center. In the center aisle. We're all being webcast, so they'd like to capture all the questions.
I got 2 or 3 questions. One, do you need the traditional ground TT&C for the CubeSat? 2, do you expect the CubeSat to replace today's commercial GEO satellite? Or maybe the third question is, where can we buy this CubeSat set to play with?
So a CubeSat, I'll start from the end. From the CubeSat, you can buy them right now. All those vendors that I showed, you can buy everything from individual parts up to actually a full spacecraft. In fact, there's a really neat one called KickSat, which is a 3U spacecraft and actually has smaller chipsats on the inside. And you can buy one of these chipsats off of Kickstarter, I believe is where it started. Put your own little program in there and it's going to spin off, and maybe you'll get a little bit of data return off of that thing. So it'll fire off all these chipsats once it's deployed from the station. It flew once. Due to a software anomaly, it actually did not work. So you know what? These things are cheap enough. They're flying it again. The second question in there was, will they replace things in GEO? And, right, will they replace DirecTV or some of the other stations that are there? And actually, no. These CubeSats are not really out there to replace the larger ones. There is so much capability, so much contextual information that you can get from the larger vehicles, so much power that's needed for DirecTV and others, that you simply can't pack that into one of the things that are this small. That would be adding additional mission requirements, and so to be able to do so, you'd have to take on additional risk or significant cost down there to miniaturize things. But the nice thing about the marketplace is every time I say that something cannot be done, such as an active radar in a CubeSat, well, now we have RainCube, and things are actually going for it, so I don't want to say never. The third question on there was, how do we actually talk to these CubeSats along the way? A slight interpretation of it. For a lot of the CubeSats, especially the academic ones, it's the ham radio operators that are out there. And if you look around on any number of roofs or in larger dishes at universities, we're talking to CubeSats there. In fact, the Radio Aurora Explorer mission, the first time someone heard from it, it was a high school student in Hawaii pointing his antenna up to the sky. And that was the first data that we received saying that the spacecraft survived. On the other hand, for going large distances, we're using the Deep Space Network. We're talking to Arecibo, which is a 300-meter dish that's out there. And we're talking to all different entities there. So we can scale the range from amateur to professional, and all of them are useful to these CubeSats.
Yeah, I had a couple of musings here. Thinking about your example with the Pluto flyby, would you be able to identify some missions in the Pluto-Kuiper area where they would go out to multiple bodies, each on their own trajectory, more of a widely dispersed kind of mission? And another possibility, is there any value that you would see in these being part of an Earth orbit, space-based solar, sort of a station-keeping perimeter around a space-based solar array?
For power down to...
direct, yeah, microwave power transmission to the Earth to get rid of all the fossil fuels and the...
I know there have been concepts out there on how we can use these in arrays and actually send power in between the spacecraft that are out there, though I don't believe anyone has looked at what that overall array would be.
Japan Space has something on the drawing board, something like 10 kilometers square.
And that is the large problem that we have with small spacecraft. And I'll address it from a constellation sense. When we're trying to send these spacecraft out there, they work well in a constellation because when any one of them goes bad, we can replace that single one rather than having to replace a very large spacecraft. The problem with power, though, along the way is that it is still dependent upon area. And we have to have a very large area, whether they be small spacecraft or whether they be large spacecraft, in order to get that power put together and get it back down to the ground. The small spacecraft would be useful as a constellation in order to replace the ones that go bad along the way. And so I can see where the concept might develop there. But in terms of the number of launches to get them up there, or at least the area that we need with the solar arrays on there, may end up being prohibitive. And that's, of course, a trade to be done later in the concept. The other question was on, do I see any missions going out toward the Kuiper Belt objects or Pluto on there with independent trajectories? Well, the problem there again is power, because power decreases so greatly as you head out there. So I don't see them independently leaving the Earth and heading all the way out there, dependent on solar panels along the way. What I do see, though, is, what I do see, at least based on today's technology, is that we use primary batteries, and that once we're out at the Pluto region, go on a trickle charge, be released, and then could individually target things along the way. Either that or using solar panels to very slowly charge the system and just have a burst back to Earth whenever they need to communicate, otherwise being in a fairly dormant state there. So there are a few different possibilities.
Oh, thanks.
One more question, piggyback on my security thing. Now, I understand, we said you can control, all are friendly, but what about rogue nations, right? I mean, we're talking about, this is such available that I can go buy on the internet. I can buy a package, put it up. What stops one of the rogue nations to contract with another rogue nations to take their satellites up?
Right.
So anyway, that almost brings back Reagan Star Wars. We need to have something on space station like a laser zapper or something that you see something you need to destroy. Like it's what Ronald Reagan was talking about, Star Wars.
For the spacecraft that might launch with a different nation that's out there, we have miniaturization of technology around the world, so of course we cannot control individual ones. But for those that we can control, there are significant regulations that have to be gone through for any country to launch with any other country on there. And in the CubeSat business, since we are in that P-pod, they actually, if we don't adhere to those regulations or if something is broken on there, they zip tie the P-pod shut. Just one of those little zip ties prevents this multi-million-dollar spacecraft from going out there. But they do actually very carefully go through the regulations and make sure that they know what's going in there and what is to be launched. You have to have launch approval from your host nation. On the second one on there, it does go back to the debris problem. And there actually have been CubeSats that have been hit by larger vehicles on there, as well as other debris that might be on orbit. Of course, we have the same problem with any large vehicle there. It's just things are becoming more accessible in miniaturization along the way. And that is one of the things that we always find with technology. We always find a way to take a new technology such as cell phones or other such things and need to be able to look at both the positives and the negatives there as we go forward. So while I don't have a definite answer on how they might address such a rogue nation, it is why we have the security industry and others out there that do look at those sorts.
This would seem to be kind of the first step or stepping stone toward what's been discussed just this last week, the Hawking's Alpha Centauri. You got any observations or thoughts along those lines?
We continued, so for those that don't know, Stephen Hawking, along with others, proposed that we actually use a solar sail to head out to Alpha Centauri with a very small spacecraft on there. And he's again taking advantage, or I should say, the foundation there is taking advantage of the miniaturization of electronics. Well, we have used off-the-shelf different pieces of hardware and assembled them together to make a CubeSat. They are looking at doing the same thing on a chip-based scale, and then looking at the feasibility of getting information back from Alpha Centauri to Earth on there. I certainly wish them luck, and I see the miniaturization of technology continuing such that such things will be enabled. However, solar sails are still in their infancy, as we've seen with NanoSail D, as we've seen with LightSail, and as we continue to test forward on there. Everything we develop for that mission will be important for our exploration of the solar system as well.
Yes, I would like to ask a question about launching capabilities. So today, if you want to launch a CubeSat, you have to go either from space station or alongside a larger spacecraft. Do you see a future for dedicated launchers? Is it something that could be useful, that could be interesting for market or something?
There is actually a market that is out there, and many companies are actually trying for it. In a very disappointing twist, one of the first, called the Super Stripey, launched from Hawaii back in January with only a few CubeSats and small sats on board, and unfortunately, the rocket failed just after launch. So just as we're going and trying to test these things with small spacecraft, the small dedicated launches are also going forward. Some of them are actually quite fun in their description, such as using a missile carried by an F-15 that goes high into orbit, launches the missile, and there is a CubeSat that's actually deployed off of that on there. That is a rapid response, and you can target anywhere you'd like to go when you have that kind of CubeSat capability. All new sorts of launches, whether dedicated from the ground or from aircraft, such as that, are being considered. And we have a question from the web. Tech Spacey asks, what is the current cost per pound to get to low Earth orbit? And what is the cost savings for launching a 1U CubeSat as compared to a larger satellite? A 1U CubeSat compared to some of the larger spacecraft that we have in the CubeSat form factor really is just a multiple of the number of U's. In fact, they'll often cost the spacecraft as how many U's do you have. For leaving low Earth orbit, it might be $1 million or more than that for a spacecraft, whereas for a 3U going up to orbit is on the order of 300 to 400,000 on there. Now, if you looked at the dedicated mass per pound of a launch vehicle, it is much more effective for you to much more cost effective to launch a much larger vehicle than to launch that same mass in CubeSats on there. And that's because the cost of launch is more than just the fuel and the rocket itself. It's all the testing, it's the paperwork, and it's all the development along the way and that interaction both with the team and the spacecraft provider that is also taken into account for the cost of going up to orbit on there. So it's more effective, cost effective to launch something large, but you can perform more missions if you launch a lot of small things.
2 questions. How do you prevent commercialization from interfering ideas within the university community? And the other question is, how are the big corporations going to make profit?
So for the second question, it's actually been interesting. Some of the corporations are looking to make a profit in terms of the launches, and some of them actually just want to cover costs. ULA just announced an initiative, and they were giving a talk at this workshop this past week, where they actually were launching several CubeSats for free from educational institutions on every one of their rockets. And then the other slots that are there, the only profit that they have is actually to pay for those free educational ones. They see it as an overall boon to the community if they can launch more vehicles up to perform more missions, either for educational training or for these other vehicles there, and they might as well make up the mass. On the first one, many of the corporations that I pointed out earlier actually come from the universities. It's the students that are developing the technology at these universities that spin off their own companies on there. And it is through a partnership that they actually continue to do so, whether it be through internships or new technology in the research bed that is the university, then commercializing out in the corporate world. The CubeSat community is a wonderful place where there are partnerships all over the place. We could not have done Inspire or Marco without our partners that are out there. And so that's where we're hoping to continue that, and why we have things like the CubeSat Developers Workshop, which is going on right now, in order to continue that effort.
Yeah.
Thank you.
I'm not an engineer or a proportional expert or anything, but is it feasible that you can launch one of these things from a hot air balloon? Like if the hot air balloon went up and then you have a rocket on the CubeSat that just pushes out to outer space?
Yes. There is a company that is trying to do just that with a high-altitude balloon, looks like a weather balloon that's essentially carrying out. And there are, as you might imagine, significant challenges there on how they might accomplish that. But all sorts of different dedicated launches are being examined.
So in this vein, how about tether?
How about the space tether?
A space tether for the tiny box like this.
So the space tether itself is generally based on a mass that is orbiting the Earth and is connected down, so you have an elevator that's actually going up. There is a history of tethers with CubeSats, mostly one that we try and tether two together for various science experiments. And virtually all of them has ended in mission disaster, where they've gotten tangled up or something has gone wrong. So CubeSats and tethers don't get along to begin with. But the space elevator has continued to be an interesting concept for low-cost access to space. What we've really found with the CubeSat is if you bring low-cost access, you can accomplish more missions, and everybody wants them to happen. If you bring it, they will come. So if the elevator actually happens, then of course we will use it to get more payload up to Earth orbit. But these things are so low in mass, they would not be able to support a space elevator, at least in the terms that have been traditionally been talked about on there. And it would require something much more massive in order to pull off that end.
One of the pieces of components that you've highlighted in the images of the various CubeSats are the processors that are on board. What are the technical requirements that that the CPUs are required to perform, and are you able to describe any models that fit the bill? Sure. So Marco and Inspire, the main flight computer on there is a small chip from Texas Instruments, TI, called the MSP430-2618. What's nice about this chip is you can find it in all sorts of things. You can find it in toasters, you can find it in razor blades, you can find it in shower heads. It's actually so small, it runs at about 16 megahertz, has about 128 kilobytes of memory and about 8 kilobytes of RAM. On the order of a little less than what was on Apollo along the way there. Yet we're able to perform our mission. Now for us, that's because it's not the only processor that's on board. We distribute our processing amongst different subsystems. The attitude control system has an FPGA that's on board that's actually running at a much higher speed, and various other subsystems handle their own technology there. But through unique and very carefully done software engineering, there isn't a whole lot that these spacecraft have to do, and that focus allows us to reduce the requirements on the processors themselves. At the same time, we have missions that are actually doing technology demonstrations for different processors that can be used on large vehicles. M-Cubed was one such mission where they actually flew a new FPGA, had never been flown in space before, to show that that processor could actually could work in the space environment and could be useful when they have thousands and thousands of megabytes that are streaming through it at any given time for enhanced science mission in the future. So CubeSats take advantage of commercial parts, things that are out there, things that are in your cell phone. In fact, cell phones themselves have been put on several CubeSats and flown. There is even one that had a finger that touched the buttons on the panel on it. So these are the sorts of things, what you see out in the commercial industry is possible to fly on these different spacecraft, assuming you take the appropriate risk and you're using it for the appropriate mission there. As we go further out with commercial components, we need to look at the lifetime in the space environment, and this is dealing with radiation, with dealing with the power. But for many missions, especially when they're trying to stay low cost, when they have a very small objective, having that small processor that can use so little power is extremely beneficial to what we're trying to do.
Sounds like you can use all the COTS components, right? So can we throw away all the space crawl MIL standards?
So it all comes down to risk. Most CubeSats on here are actually flying commercial off-the-shelf or COTS components, but it's because they're willing to take additional risks because they want to keep that cost number low. And they also don't need to handle the robustness of larger spacecraft. If you have a $500 million spacecraft, you want it to survive, you want it to work, you want to test and make sure that it actually will work. And as part of that testing process, you test the parts all the way down to the individual components to make sure that they will survive and work along the way. Now, those are space-hardened parts. These are parts that we know tolerate radiation. They have been through environmental testing. They've been through all sorts of analyses. That raises the cost. So the very fact that you want to build for a $500 million mission itself makes it a $500 million mission. With a CubeSat, we're staying low cost because we say we have a fixed budget. If you're building your kitchen, you have one budget that you can go with, or else you won't have a kitchen. You can't cook your food. I can't fly my spacecraft. So we have to make those risk trades on there, and it's because of that that we often choose the commercial off-the-shelf parts.
And on those cubes, like, that does have a battery life as well, right? And what is the estimated time like until the failure of it?
In terms of lifetime of the battery, it's usually that the batteries can survive for at least several years on orbit. We saw with Psi-4 that the mission is still operating after 13 years on orbit on there. But we do go back to the manufacturer specifications to see how it does. We also treat our batteries very carefully along the way. For instance, on Marco, which has a 26-month shelf time now, as we're waiting for launch, we have to check in on the batteries and actually keep them at a regular charge every 3 months or so. So it's doing things like this.
Is there any plan to send those boxes, cubes, back into the Earth? Is there like any future thoughts about it?
So there are several CubeSat efforts that are actually looking at how can we return things from orbit. With a small spacecraft, you don't get a lot of data down, and for some of the missions, you're actually acquiring a lot of data. And so because of that, there's actually been the idea of, well, there's an SD card that's storing data on board. Why can't we bring that SD card back down to Earth? The problem in general has not been getting it down through the atmosphere. It's finding it afterwards, because there's a lot of ocean out there. So there are a number of companies that are out there, and they have published from Aerospace Corporation to various universities and such that are actually trying to go forward and do some kind of return from orbit from CubeSats. Still to come.
Why not put some charging stations up in space? So when you go out further, they're nuclear powered or something, and then when the CubeSat has reached its certain battery limit or gone out further, they can get recharged at these stations and go further.
So for all of these things, and there's been talk about fuel depots throughout the solar system for our larger spacecraft along the way. It depends on what we want to use these craft for and how much money would it take to actually put a charging station out there, and what is the actual benefit that you would get with these CubeSats as they go further out. We found with our larger spacecraft that in the outer solar system that we typically go with these radioelectric generators that we have on board, RTGs, radiothermoelectric generators. And that allows us to have power much further out. Voyager, of course, is using these along the way. For CubeSats, so far, their most useful spot has still been in the inner solar system because there are so many desirable targets that we have yet to hit, plus the power and thermal and all the other challenges that you have as you go further and further out. For now, I foresee that CubeSats are primarily going to be the disposable probes of space, such that we won't necessarily need to recharge them, and that we'll have the larger motherships along the way that either will carry the RTGs and can charge before deploying these things, or that we will find other methods of kind of deploying them or running with power later on. Any last questions?
Thank you.
Thank you very much for coming tonight.